Hey everybody, now I have Excel open in front of me. We're going to use Excel to basically solve the same problem that we just did a few minutes ago, paper pencil. Now Excel will accomplish the same thing. So here the variable x and y's are given. So the way we should understand them, they are pairwise related. So we have 5 observations, observation 1, 2, 3, and so on, 4 and 5. You can imagine x and y are something like maybe x is years of education, y is income level. So as a result, you go ask the first person how many years of education you have, what's your income. Person 2, how many years of education you have, what's your income, and so on. Awesome. So I will directly use Excel's built-in data analysis function tool. So you go to data analysis ribbon as usual. So regression is selected here from the drop-down menu. We select the regression analysis here, press OK. And now we are going to, let me just delete all this. There we go. Let's just remove all that and remove that as well. So let me make sure I explain each one separately. So we start with the dependent variable. Y is referred to as the dependent variable. So it's this column over here. So select it and there you go. The independent variable is x. There you go. Labels are selected because the data includes label, column headers basically. And finally, what we can do is we can plot some the residuals. So I'm going to remove this one. All I want is the line of best fit. And let me see. Yeah, that's pretty much it. I want the output to be on the same document. So starting at D1 here. Finally, there's this also option of confidence interval. By default, there's a 95% confidence interval built around the parameters, estimated parameters. So if you're fine with it, then you don't need to use this one. But if you need, like, the default is 95%, but if you additionally need another one like 99%, for instance, you can click that as well. So I will have it clicked just to give you an idea how it works. And that's it. So just press OK and boom. So you can see regression results presented already, as well as the plot. The plot is missing the regression line. So let me just go ahead and let me just yeah, let me make it a little bit larger. Okay, wow. Okay, it's good. So select the orange ones. These are the predicted values. So you want to add a trend line and make sure it's a linear. And you guys can go ahead and change it into the same color. So solid line. Yeah, I think this color is good. And let's make it a bit thicker. There you go. So this way, not only we have the predicted values, we have also the linear relationship. We did draw the line. So the original given values were these data points here, the x's and the y's here, were the blue points. And so we have fit a straight line onto it. Awesome. So let's go to each question separately. So for the first question, the question was to find out the estimators beta 0 hat and beta 1 hat, the intercept and the slope parameter. And here so there are 3 tables given to you: the first table, the second ANOVA table, and the third table. All right. So here we will be focusing on the third table for the coefficients here. So these are the parameters that we are estimating. The intercept is 1. And the the slope parameter is 0.7. So this is beta 0 hat, and this is beta 1 hat if you want. All right. So these are the 2 values. Actually, let me just write it next to it. Beta sub 0, and this one is beta sub 1. Awesome. So, wow. So these are exactly the same values. Let me go ahead and highlight them. These are exactly the same values that we predicted, 0.7 and 1.0. Next question. Question was asking for the variances. Well, there's nothing much we can do here because we have not calculated sigma yet. So let's scroll further down, then we can come back to this in just a minute. Actually, yeah, so we'll come back to that. Next is asking for an estimate for sigma square. We found out that the estimate, we realized that S square was an unbiased estimator for sigma square. So S square, when we calculated it, we found out to be 0.367, where SSE first of all came out as 1.1. So what we can do, and SYY came out as 6. So we can just go back to the Excel. So you guys can see the SYY and the SSE. Do you guys see that? Those two? It's pretty cool, so let me highlight them. And finally, like we said, the S square was 0.367, and there you go, 0.367 is also part of the Excel report that is being generated. And then later on, I think we even learned how to take the square root of this, and this was the sigma itself. The square root of this number comes out as this number, 0.606, so that's another number that we understood. By the way, I forgot to mention that SSE, when we calculated it, I think we were mentioning about 2 degrees of freedom, so n-2 here. Sorry, 3 degrees of freedom, that's why we use n-2, and those degrees of freedom is right here for the residuals. So the residuals have 3 degrees of freedom. I think we mentioned it somewhere. Let's see, degrees of freedom. Yeah, I'm not sure exactly, but I know I mentioned it, but yeah, so somewhere I mentioned it should be 3 degrees of, oh, say there you go, n-2 degrees of freedom for the test statistic. Well, in this example, we realized that the z-test suddenly, because sigma is not known, the population standard deviation, the moment we use the s to predict the sigma, then suddenly the z-test turns into a student's t-test, and the student's t-distribution will use an n-2 degrees of freedom. All right, so n is 5, 5 minus 2 is 3, that's the degrees of freedom for the residuals. Awesome. What else was the question? So we talked about this, we talked about s squared, so the 0.367 right here. What else? What's the next question? The hypothesis test. So are the results significantly different from 0? So we ended up calculating the student's t-test statistic, 3.65, and sure enough, the t-test statistic 3.65. Do you see that here? So it's pretty good. So with that 3.65, we were able to say that the slope parameter 0.7 is significantly different than 0. The same thing with the y-intercept. It's also significantly different than 0, though we didn't calculate it. In addition, you could have also calculated the p-value, which is also, it turns out to be very straightforward. It's just a probability that you calculate at the threshold. And if you did so, you would have seen that the probability for the slope parameter is 0.035. And because this number is less than 0.05, the significance level, again, we reject the null hypothesis that beta 1 is 0. It's not 0, it is different than 0. Okay, good. So therefore, we were able to calculate this number as well. So pretty good. What else did we do? So let's scroll. And then finally, we came with the 95% confidence interval. And so this interval we realized was between 0.09, so this number here, and 1.31, which is this number over here. So 0.09 to 1.31, in fact 0.09 to 1.31, so these numbers. So about these ones, remember earlier I mentioned when we did the regression analysis, when we selected the data, it gives us the additional option, let me show you one more time, to choose an additional confidence level. But by default, the 95% is always calculated. So this one comes by default, but if you want an additional confidence interval, so you can attach it here. So this one was not necessarily needed for us. So let me just delete it by shifting the cells to the left. Okay, good. And what else? Well, we could have similarly find the confidence interval for beta 0 as well. And if we did so, we would have found this, but it's very straightforward. Yeah, that's pretty much it, I guess. Let me see if we talked about all these. So one thing you can do is, because we are predicting sigma square by using s square, you can 0.367. So you guys can substitute it here, 0.367, and divide by 5 to find the variance. And the same thing, divide by 10 to find the variance of beta 1. I wonder what these numbers are equal to. So let me, hold on a second, 0.367, right? 0.367 over 10, and let me take the square root, equals 0.367 over 10, and I want to take the square root of that number, because that's a variance. So 0.19, hey, look at that, that's this number over here, the standard error. So you might as well find the standard error So it is just the square root of these two numbers would be we found the variances of the estimators, but the standard errors are just the square root of those values. So yeah, pretty neat actually, where you replace sigma square with what we found in the next step, which is s squared. So we even calculated these numbers in a sense, right? So that's very neat. Let's highlight this. So we pretty much have a very good understanding of the whole thing. A couple of things that I skipped alongside, let me just explain. So what about these values? So in this example, the f-test is not that important because the results turns out to be the significance of the least square method with just one variable turns out to be the same as the p-value here. And we already used the p-value to check if the beta 1, the slope parameter, is significantly different than 0. And we established it is. So therefore, but in general, you can check the f value and the significance level. If that f value is high and this thing is low, it means the test is, the regression analysis is good. So the analysis of variance, that's what it is for. And finally, the R square, something that I should mention as well. This number here shows how good of a fit our model is to the data. So in a sense, you can interpret this as we can say that 81% of the variation in the data can be explained with the independent variable x. So 81% of the variation in y can be explained with the variation in x. Obviously, they are not one-to-one exactly correlated. If they were, the blue points here, they would be exactly on that orange line, which they are not. But still, it's the plot is pretty good. In fact, this one is exactly on it. The line goes through that point 1 as well. But yeah, so this is the way we interpret this R square. It turns out R square is an important number that we end up calculating and using. So again, 81% of the variation in the dependent variable can be explained with the variation in the independent variable x. Let me actually write this down here. 81% of variation in y can be explained with variation in x. So 81% of the variation in y can be explained. So 81% is pretty good. There's still a 19% that needs to be explained. For instance, what if x is years of schooling and y is income level? So you are saying that you can explain 81% of your income with the number of years of education that you got. But obviously this is not one-to-one. There's the chance factor. There's other factors like gender, for instance. It might be effective, or geographical location might be effective. If you live in New York City, obviously you can expect to be paid more than if you are living in Arizona, right? The salaries therein are much higher because the cost of living is much higher in New York compared to Arizona, for example, and so on. So, but 81% by itself is a pretty 81.6, or like close to 82% actually, is very so it has a lot of explanatory power. So this X has a lot of explanatory power. That's it. So hope this was useful. So basically this is how we do a regression analysis using Excel. Now that you know all these, you should be able to attempt the assignment problem. Thank you.